If you've come to have a look at a video talking through June 2008 Paper 2 AQA GCSE Maths Foundation tier, you're in the right place. According to when I'm making this video now, this one was sat less than 2 weeks ago. So it's very current, and it is a calculator paper as well. So you should have on you a scientific calculator, and a good one at that. Personally, I recommend the Casio one, which I'm going to show you later, but it's up to you which one you get, but I would heavily recommend the Casio. Without a scientific calculator, you're really not giving yourself a very good chance, or in my opinion, taking it as seriously as you should be. Anyway, let's have a look at question 1 and see how we get on. Question 1, circle the expression that can be written as 2y. So 2y, we need to know what 2y means. And 2y, because there's no instruction in between the 2 and the y, that'll mean 2 multiplied by whatever y happens to be. So it's 2 lots of y. So we need to circle the expression which is the same. And so what we can do is we can also, if we can, simplify these and see which one would be the same as 2y. So y squared, well, that means y multiplied by y. That means y multiplied by itself. 2 plus y is just as it is. Y multiplied by y is the same as y squared, and so this one is the same as this one here. But y plus y would simplify to 2y, which is what we've got here. So the one we need to circle is y plus y. Another way you could have thought of this is just pick any number for y you'd like. So for example, if you pick y to be 10, if y was 10, then 2y would mean 2 times 10, which is 20. And if you're still having y equals to 10, then the only one of these expressions which would also equal the same, the only one of these would also be 20, would be this one here, because 10 plus 10 would also give 20. The reason I'm labouring question 1 a bit is because it's really, really important you do well on these first questions to get your grade 4. So question 1, we need to circle y plus y. Question 2, circle the decimal that is greater than 3/10 and less than 2/5. So if we have a look at the decimals we've got here, we've got 0.32. In fact, they're all decimals. So what we could do is change these fractions into decimals and then compare. So 3/10, we could type in the calculator, 3/10, press equals, and then change this into decimal form by pressing this S arrow D button. And we get 0.3. So 3/10 is 0.3. And 2/5 we can change in the same way. Type in the fraction as it looks, press equals, and change. We get 0.4. So you can think of this question as which one of these decimals is in between 0.3 and 0.4. And if it helps, you can think of this as 0.30 and 0.40. Because there's no digit next to the 3 or 4, so we can interpret these as invisible zeros. So which one is between 0.30 and 0.40? It's got to be 0.32, because that's more than 0.30 but less than 0.40. So the one we need to circle is the first one. This one here, 0.035, to the nearest, say, penny in terms of decimals, in terms of money notation, that'd be roughly 3p. It'd round up to 4p. It'd be 0.04 if we rounded it to 2 decimal places. That's much less than 0.30. 0.4 is the same as this one, so that wouldn't be less, that's the same as, and 0.24 is less than 0.30. So the first one is the only one that's between these two. Question 3. What is 625 as a power of 5? What this question means is 625 will match to one of these numbers. So let's see which one it would be. So your calculator has a built-in power button on it. On this calculator here, it's the X with a floaty square next to it. So 5 to the power 3 is 125. So that's too small. If we try the next one, 5 to the power 4, we get 625, which is correct. And so the one we need to circle is 5 to the power 4. That one's too big, and that one is massively too big. So the answer we need is 5 to the power 4. That's 625. So we circle this one. Question 4. Circle the order of rotational symmetry of this drawing. The order of rotational symmetry, all it means in plain English is it's just the number of times that the shape looks like itself. I'll explain this in a second. It's the number of times the shape looks like itself in one complete turn. So look at the shape as it is right now, and imagine it being turned around. How many times will it look like itself in one complete turn? So to help you with that, to help you picture it, I've just copied the diagram across, and I've put the diagram with a red spot on top of it. And so if I just take this drawing here and put this with a red spot on top, what we're going to do is just superimpose this drawing on top of this one, and then we're going to see how many times this one looks like itself. So if we just group these together. So there, you can see that it's on top. So now if we turn it round and keep an eye on this red dot, when the red dot gets back to the top position, we've done one complete turn. So that's once, twice, 3 times. The triangles don't perfectly overlap, but hopefully you get the idea. 4 times, 5 times, 6, 7, and back again is 8. And so this shape looks like itself 8 times. So the order of rotational symmetry of this shape is 8. And so that's the one we need to circle. Question 5, we need to work out the value of this calculation. So 3 to the power 6 minus the square root of 841. I'm just going to show you how to do this in one step on your calculator, just to make it as efficient as possible in terms of time. So 3 to the power 6, we type 3, power button 6, minus, this is the square root symbol, so we press here, the square root of 841. Press equals, and you should get 700 exactly. So the answer for question 5 is that this calculation is exactly the same as 700. Question 6, we've got Gemma with 4 groups of friends on a social media site, and the table shows the number of friends in each group. So what we need to do first for part A is find out which group is the mode. Well, the mode means most common. So if you had a list of values, the mode would be the value which shows up the most. In terms of a table, the mode will be the group with the most items inside it. And so the group, which is the mode, the group with the most stuff inside it is the school group, because 26 is the highest number of friends out of all of these different groups. And so the mode we need to just write down is school. For part B, Gemma wants a pictogram to show the information, and she's drawn the first 2 rows. And so if we try and complete this pictogram, we need to include a key. Let's just have a look at the family, for example, first of all, so we can work out what each circle represents. So for family, or netball in fact, you could have picked either. We've got 8 friends. And for family, we've got 2 circles. And so what we know is that those 2 circles must represent 8 friends. So if 2 circles represent 8 friends, each one individual circle, must therefore represent just 4 friends. And I've done that just by dividing both sides by 2. Half of 2 circles is 1 circle, and half of 8 friends is 4 friends. And so that's how we need to complete the key first of all. So it represents 4 friends. So what we need to do next is to fill in for school how many circles are needed, bearing in mind that each circle represents 4 friends. And so I've got symbols here which we can use. And so first of all we need 4. We need to go up to 26. So 1 circle's 4, a second circle would be 8, and 12, 16, 20, 5 circles is 20, a 6th circle takes us to 24. Now we want an extra 2 friends. To go from 24 to 26 is an extra 2. If 1 circle's 4 friends, we need half a circle to represent 2 friends. And so the next thing we do is get half a circle here and draw that in. I'm just cheating really by copying them across. Your diagram doesn't have to be perfect, but you need to show your circles clearly and make sure your circles are circular enough so that your full circles aren't mistaken for a semicircle. So you don't need to be a Pablo Picasso when you're drawing these, but try and be as accurate with drawing your shapes as you can. For final row, guides, we have 11 friends. And so what we need for guides is 2 complete circles, which takes us to 8 friends. And to get from 8 to 11 friends, we need a final 3 friends. If a full circle is 4 friends, half a circle would be 2, and a quarter of a circle is 1 friend. And so for 3 friends, what we need is 3/4 of a full circle. So the final one for guides is we need to include a symbol, which is 3/4 of a circle. And that's part B of question 6 done. Question 7 is about expressions. Now, by expression, it means something in algebra where we don't need an equal sign for it. And so E is 3 more than D, is what we're told here. And F is 5 less than D. And so we're asked to write an expression for E in terms of D. So if E is 3 more than D, then what we could say here is that E is whatever D is plus 3 more. But because we need an expression, that means we don't need an equal sign. So we can just say E is D plus 3. So the answer to this one is D plus 3. Another way of thinking about question 7, obviously we've got the answer that E is d plus 3. But we could picture it as well on a number line. So if we just imagine a line where we've got smaller numbers down on the left and bigger numbers on the right, and we've got d somewhere in the middle, then if we're told that e is 3 more than d, what that would mean is that e is 3 to the right of d. So 3 more than d would be 1, 2, 3. So e would be here. So whatever d is, e is just d plus 3 along. Part B, we need to write an expression for f now in terms of d. So f is 5 less than d. So whatever d is, f is d take away 5. And again, in terms of a number line, which will be much more useful in a second, for part C, if you imagine it like this, so we had that e was up here. If f is 5 less than d, unlike e, which is 3 bigger, f is 5 less, and so from d we'd go 5 in the small direction. 1, 2, 3, 4, 5. F would be right at this end here. So f is wherever d is, but we need to take a further 5 away. Whereas with e, we did d and added 3. Let's have a look at part C next. It says to work out e minus f to simplify your answer. I'll do this purely algebraically, and then I'll show you how a number line would really help, I think. And so if we just think about what e is, from before, from part A, we worked out that e we could write as d plus 3. And so e is d plus 3. Then we're going to take away from that whatever f is. And from before, we said that f is d minus 5. And so e minus f means d plus 3 minus d minus 5. So now if we work this out and try and simplify it, with d take away d, the d's would cancel. D take away d is 0. So nothing to worry about for the d's. But for the units, we start with 3. Now we're going to subtract minus 5. 3 minus minus 5 is the same as 3 plus 5. If we've got two minus signs right next to each other, two minuses make a plus. So 3 minus 5 is actually 8. So the answer to what e minus f is, e minus f would be 8. Now in terms of a number line idea, which we saw for parts A and B, a number line makes it just much easier to visualize. So going back to what we had before, e was 3 more than d. So e is 3 to the right, which is here. Then f, which was 5 less than d. 2, 3, 4, 5. We worked out f would be down at this end. The next thing is just to remember what subtraction tells you about two different numbers. If you do e take away f, subtraction tells you the difference between them. So e is the bigger number, f is the smaller number. So if you just have a look at this number line and think of it, what's the difference in between e and f? It just makes it much simpler. So just to remind you what I mean, e minus f, just just means the difference between E and F. Looking at this number line, we can see much clearly than using the algebra that E is 8 bigger. The difference between E and F is 1, 2, 3, 4, 5, 6, 7, 8. E is 8 on the bigger side compared to F. So when using a number line, it might make it much simpler to see. Question 8 is a bit of a mathematical puzzle, really. The numbers 1 to 12 are put in a grid. We've got 2, 4, 5, 7, 10 and 12 already in the grid. And each of the 4 sides of the grid must add up to 26. It says complete the grid using the numbers 1, 3, 6, 8, 9 and 11. The key bit of information here is that each of the 4 sides of the grid must add up to 26. And so, if you look at the left-hand side, we can easily enough work out that this number must be at the top. Just looking at the left-hand side, these 4 numbers need to add up to 26. So 7 plus 4 plus 12 plus whatever's in the highlighted green space needs to add up to 26. So if we add together 7 plus 4 plus 12, that gives us a total of 23. And so 23 plus whatever the green one is equals 26. And this is a simple equation to rearrange or solve. So what number, when we add it to 23, would give us 26? The answer, of course, must be 3, because 23 plus 3 would give us 26, like we need. In terms of thinking of it as algebra, we can swap side and swap sign. That 23 is a positive number. If we move it across, it will swap to being minus. 26 minus 23, as I've just said, would be 3. And so that top number is 3, and so we can now cross off 3 because we've used it. Now we can work out the top row, because if I look at the top, 3 plus this one plus 5 plus 10 must add up to 26 as well. In fact, I'm just going to use a different colour than that one. I'll use a light blue colour. So just looking at the top row, all of these need to add up to 26. So if we neaten this left-hand side of the equation up slightly, 3 plus 5 plus 10 gives us 18. And so 18 plus the blue one would add up to 26. And so 18 plus what number would give us 26? The answer to that would be 8. Again, the same way we can think of this 18 as swapping side and swapping sign. The opposite of positive is minus, because 18 is a positive number right now, so when it swaps it changes to minus. So the blue one will be 26 minus 18, which would be 8. And so we now got 8, and so we can cross off 8. So we've still got other numbers to use. We've got 1, 6, 9 and 11. And so if we have a look at the bottom row now, 7 plus this one plus 2 plus this one needs to add up to 26. 7 plus 2 is 9. And so 9 plus the other two boxes will be 26. And so in case of swapping side, swapping sign again, if that 9 moves over and swaps to the 26, it will swap its sign to a minus. 26 minus 9 would be 17. And so for the bottom row, these two mystery numbers need to add up to 17. And so which of these numbers, 1, 6, 9, 11, which two of these add up to 17? And the answer to that is, in some order, it's 11 and 6. So maybe 11 goes here and 6 goes there, or maybe the 6 goes here and the 11 goes there. We don't know, but we can try it now. Now we know that 6 and 11 must go on the bottom. We know that 1 and 9, the only two numbers left, must go on the right. So if we just double check this works, 10 plus 1 plus 9 plus 6 is 26, so that works. And along the bottom, 7 plus 11 is 18, plus 2 is 20, plus 6 is 26. And so we've got all the numbers in the right places now, and this puzzle now works. And so question 8 has been complete. Question 9, we need to do a conversion. We need to change 5 feet 8 inches to centimetres. So first of all, if we have a look at these conversions here, we've got that 1 foot equals 12 inches. So once again, as seems quite common, we have a conversion factor where one number is a 1, the other number isn't 1. If we have a relation, a ratio, where one number is a 1, the other number isn't a 1, we can change from one thing to the other by either multiplying or dividing by the number that isn't 1. So in this case, we're either going to be multiplying or dividing by 12 to convert these units. If we're going from feet to inches, we're going from a small number to a bigger number. 12 is bigger than 1. And so what we'd have to do here is multiply by 12 to change from feet to inches. Again, the other way around, from inches to feet, we go the opposite way, we do the opposite thing. Opposite of multiplying by 12 would be dividing by 12. And so first of all, what we could do is change 5 feet into inches. So 5 feet, oops, I'll do an arrow instead of that red line. To change from feet to inches, we could multiply by 12. And the reason we're multiplying by 12 is because of what we said earlier. 5 times 12 is 60. And so 5 feet is the same as 60 inches. So what we know now is 5 feet 6 inches that's the same as altogether 60 plus 8 inches, because 5 feet is 60 inches. And 60 plus 8 is 68 inches. Luckily, we've been given a conversion factor to change from inches to centimetres as well, which is this one here. So we're told that 1 inch is 2.5 centimetres. And once again, if you have a look at this conversion factor, this conversion relation, we've got one number that's 1 and another number that isn't 1. So yet again, as we had here, we can change from one to the other by multiplying or dividing by the number that isn't 1. In this case, we multiply or divide by 2.5. So if we're changing from inches to centimetres, we're going from a smaller number here to a bigger number there. So we'd be multiplying by 2.5. Whereas if we went the opposite way round and we were changing from centimetres to inches, we'd be going from a big number to a smaller number, and then we'd be dividing by 2.5 instead. But in this question, we're wanting to change to centimetres, and so we're going to be going from left to right. So we're going to multiply the inches by 2.5. So 68 inches, if we times that by 2.5, we'll have our answer in centimetres. So just need to get out your calculators and do 68 times 2.5 and see what we get. So for this one, 68 multiplied by 2.5 gives us 170. And so 5 feet 8 inches in centimetres is 170 centimetres. And that's our final answer for question 9. Question 10. Which of these numbers has exactly 4 factors? By exactly it means no more or no less. So we need to circle the answer. So first of all, if you have a look at 4, what can we divide 4 by? We can divide 4 by 1 and by 4. Any number can be divided by itself and by 1. But 4 we can also divide by 2. But 4 divided by 2 is also 2. And so 4 only has 3 factors. So it's not 4. If we try 8, again 8 can be divided by itself, which gives 1, or 8 divided by 1 gives 8. And we can also divide 8 by 2. We can half 8, which gives us 4. And there's nothing else we can divide 8 by. So 8 does have 4 factors. Exactly. So 8 is the one we need to circle. If you're unsure, you could always check the others, not that you'd have to if you're confident. But 12, well, we can divide 12 by a few things. We can divide it by 1, which is 12. 12 can be halved. 12 divided by 2 is 6. Finally, we can also divide 12 by 3, which would give us 4. And so 12 would have a total of 6 factors. So 12's got more than 4 factors. And finally 16, as ever we can divide it by 1, which gives us itself. 16 is an even number, so we can half 16, which gives us 8. And lastly, we can divide 16 by 4, which gives 4 again. So 4 is a repeated factor, just as 2 was a repeated factor with a number 4. And so 16 has 5 factors. So the only one of these 4 options with exactly 4 factors is 8. And so just to mention again, that's why we're circling 8 for question 10. Question 11 is about Nick's code. So he remembers it as 3 2-digit numbers. The first number is between 10 and 20, the second one is 3 times the first, and the third number is 5 times the first number. And so let's just highlight that bit of information because that is going to prove to be important. So the second number is 3 times the first one, and the third number is 5 times the first one. As well, all 6 digits are different, so the digits in the code can't repeat. So we need to work out the code. As long as you do this systematically, it's not as hard as what it may seem. And so what I'd suggest doing is a careful trial and improvement method, something along the lines of this, although not necessarily exactly the same. So we know that the first number is between 10 and 20, and so what we can do is just list down for the first number the different possible values of it. We can just try the different numbers until we get the code that works. So if the first number was 10, the second number is going to be the first one times 3. And so if you get the calculator and just do that calculation, 10 multiplied by 3 would be 30. But we can't have that because the digits have to be different. All 6 digits have to be different, and here we've got the 0, which has been repeated. And so the first number can't be 10, because if it was, the 0 would repeat. In the same way, before we even begin, it can't be 11, because you've already got 2 ones which have repeated. So 11 isn't a possibility. Could 12 be? If 12 were the first number, the third number would be 12 times 3, which is 36. No digits have repeated yet. But the third number would be 12 times 5. And 12 times 5 would give us 60. And so it can't be 12 either, because the 6 repeats in 36 and in 60. 13 perhaps? The second number would be 13 multiplied by 3, which would be 39. And so it can't be 13 because the 3 would repeat. 14. 14 times 3 for the second number would give us 42. And so if 14 was the first number, the number 4 would repeat. So again, the number can't be 14. Just keep going and we will get there eventually, as boring as it might seem. 15 multiplied by 3 is 45. The 5's repeated, so the first number can't be 15. 16 perhaps? If you were to do 16 multiplied by 3, you'd get 48. But 16 multiplied by 5 would be 80. And so the 8's will repeat. If we try 17, 17 times 3 would be 51. So the 1's have repeated. It's surely got to be 18, 19 or 20 now. There's only so many numbers it could be. So 18. If the first number was 18, 18 multiplied by 3 would give us 54. And the third number would be 18 multiplied by 5, which would be 90. Now if you have a look at this code here, do any digits repeat? The answer is they don't. All these digits here on this row are different. 18549 has no repeated digits, and it follows the rule that the second number is 3 times the first one and that the third number is 5 times the first. And so we've got our code here. We finally found the one that works. So the full code is 185490. Question 12. How many minutes are there in 5 1/4 hours? I'll show you a couple of ways of doing this. One way is just to think of an hour as 60 minutes, which I'm sure you all know. But because we've got 5 whole hours, to go from 1 hour to 5 hours, we could multiply by 5. And so if we multiply this side by 5, we'll need to do the same to the minutes. 60 multiplied by 5 would give us 300. And so 5 hours gives us 300 minutes. And a quarter of an hour, if you're going to be a quarter of an hour late, or a quarter of an hour really, a quarter of an hour is a quarter of 60, which is 15 minutes. And so in total, 5 and a quarter hours, 5 and a quarter, is 300 minutes plus 15 minutes, which gives us 315 minutes. So 5 and a quarter hours, the correct answer to this one is 315 minutes. So that's the one we need to circle. Another way we can think about this is using the fact that 1 hour is 60 minutes. We've got a conversion factor to change directly from hours to minutes. Because this conversion relation is in the form where one number is 1 and the other number isn't 1, we can change from one unit of time to the other by simply multiplying or dividing by the number that isn't 1. So in this case, we're going to be multiplying or dividing by 60. So if we want to change from hours to minutes, we're going from a smaller number to a bigger number. So to do that, we'd have to multiply by 60. And so we can take 5 and a quarter, which is our value of hours, and multiply that by 60, as long as we know how to use the calculator correctly. So I'm essentially just doing this as an excuse to show you how to use a mixed number button on your calculator. A common mistake people will do is they'll type in a quarter, then skip back and type in a 5 in front. That is not how you type in a mixed number, although I can understand the temptation. What you'll need to do to type in a mixed number directly into your calculator is to press Shift and the fraction button. And you should have this symbol with 3 boxes coming up. The whole number goes into the first box, and the fraction part of a mixed number goes into the other 2 boxes. Like this. So 5 and a quarter multiplied by 60 is 315. So that's just a different way of thinking about it. But we still get the same answer. Either way around we do it. Question 13, we've got a formula for the amount of water we need to cook some rice with. And so W is the number of cups of water needed, and R is the number of cups of rice to be cooked. So for part A, we need to work out how many cups of water are needed to cook 7 cups of rice. So cups of water is W. The cups of rice are given by R. So if we want to work out how many cups of water, we're wanting to work out W. And so this is the formula for working out how many cups of water we need. It's 1.5 next to the R. 1.5 next to R means 1.5 multiplied by R. So we're going to be working out how many cups of water. So we do 1.5 multiplied by the number of cups of rice we need, which in this case is 7 cups. And so we do 1.5 multiplied by 7, and then we add on 0.5. So if we do that calculation, 1.5 multiplied by 7 plus 0.5, you should find that we need 11 cups of water. So the answer to part A is we need 11 cups. Part B, we have the same equation exactly, But this time we're needing to work out how many cups of rice can be cooked with 20 cups of water. So I'm going to show you two different ways of tackling this question. So one way we can do it is just by rearranging the equation. And so if we've got 20 cups of water to cook with, then we know the value of W is 20, because W represents the number of cups of water. So just substituting in 20 for W, we'd have 20 equals 1.5 R plus 0.5. We now have an equation in terms of R which we can solve. To solve the equation, we want to have R on its own. So the first step we could do is to get rid of this plus 0.5. This 0.5 is a positive thing. If we get rid of it by swapping it to the other side of the equation, if we swap the side, we swap the sign. Opposite of plus is minus. And so on this side we'd have 20 minus 0.5, which should give us 19.5. And on this side of the equation, we'd just be left with 1.5R. Now that R is being multiplied by 1.5, but we don't want 1.5R, we want to have R on its own. So we can get rid of this 1.5. That 1.5 is multiplying the R, so if we swap the side, we'll swap the sign to the opposite of what it's doing right now. Right now it's multiplying, so when we swap the side, we'll swap it to the opposite, which is dividing. And so R equals 19.5 divided by 1.5. Which is 13. So we can cook 13 cups of rice using 20 cups of water. Another way this could be done, just to show you another method, is we can start the equation off with what we're wanting to find out. So we're wanting to find out how many cups of rice we can cook, which after all is what R represents. So using this flow diagram method, we can start with R and then take it step by step and think what happens to R. So the first number that R bumps into is 1.5, and that 1.5 multiplies R. So the first thing that happens is that R gets multiplied by 1.5. After being multiplied by 1.5, we then add on 0.5. Oops. So if we add on 0.5, that's the next step we get. And after we add on 0.5, nothing else happens. What comes out of the other end is just what W is equal to. We're told in this instance that W is 20 cups of water. Now all we need to do is reverse each step of this flowchart, start at the end, and go the opposite way, working back to the beginning. But because we're going to be doing the opposite way, we're going to be doing the opposite thing each time. So here, the last thing we did, was to add 0.5. So if we are going the other way, instead of adding 0.5, we'll be subtracting 0.5. 20 take away 0.5 would give us 19.5 at this stage. then instead of multiplying by 1.5, the opposite of multiplying by 1.5 would be to divide by 1.5. And so r would be 19.5 divided by 1.5, which comes out to be 13. And so r equals 13. A final way I'll show you is we can substitute into the formula as many times as we want, and by trial and improvement we would eventually get the answer. W is going to be 1.5 multiplied by whatever r is. So maybe we could guess it's 8, then always plus 0.5 at the end. That was 12.5. But we know that it should come out to be 20 cups, so 8 was too small. So we could go back and guess 9. Change it to a 9. 14. Still not 20, so increase again. 15.5. Still not 20. Increase again. 17. Still too small. Change the 11 to 12. It still isn't 20, but if we go one final time and try the value of 13 for r, so 1.5r, 1.5 times 13, then that is the value of r which works and gives us that the cups of water would be 20. So 20 cups of water, 13 cups of rice. So you could do it the long way, just using your calculator efficiently. So for question 13, I've just shown you there 3 different ways you might want to attempt that one. But that's all there is to say really about question 13. Question 14, we're told to use our calculator to work out the value of 9.95 squared multiplied by 29.8. We're told to give the answer as a decimal and to write down the full calculator display. And so understandably this is only 1 mark, because if you now choose your calculator, this should be very simple. So we type in 9.95, then most calculators, including this one I'm recommending, will have a squared button on to press. Then we multiply that by 29.8, and the answer we get is 2,950, which I just need to write down here before then reminding myself what the decimal part was. And then we had after 2745. So 2950.2745. And that's the full answer. Now for part B, we're asked, is the answer sensible? Use approximations to decide. You must show you're working. But just think about this for a second. You've been given a calculation to perform with a calculator. There's no strings attached. It's not a calculation you've had to come up with yourself. You've not had to guess what the question means. It's a question they've told you to type in on the calculator. And you need to be assuming at this stage that you know how to use your calculator. If you do a calculation on your calculator, which is exactly as the exam asks you to do, and you press equals and you use your calculator correctly, the answer will have to be sensible. The only way the answer won't be sensible in this case is if you've made a mistake on your calculator. So have some faith in yourself and just tick it must be sensible. It's got to be, unless you've mispressed and done, like, I don't know, let's say you may have done 995 squared instead of 9.95. Anyway, it's a case of proving why it's sensible. And the key word here is approximations. And so what we're going to do is we're going to take the initial calculation, which was 9.95 squared multiplied by 29.8. And the answer we got for that one was 2950.2745. If a question says to approximate or to estimate, it's almost a clue. The question's telling you to round the values off. not round off at the end, but to round the starting values. And so 9.95, that's going to round fairly easily to 10. 9.95 to the nearest whole number, we can call that 10. So instead of saying it's 9.95 squared, we can estimate it as 10 squared. And in the same way, 29.8 is very, very close to 30. And so if we round 29.8 to the nearest whole number as well, and call it 30, let's see what the answer would be if we use these rounded values in our calculation instead. 10 squared multiplied by 30 gives us 3,000. So let's compare the actual calculation at the top to the rounded calculation we've done up below. So if you can compare these two, then this should clearly show why the answer is sensible. 2950.2745 is very close to 3,000. So 2950.2745 is very close to 3,000. Now, our approximation was higher. The approximation is a little higher, but that's understandable because think about what we've just done. .95 we changed to 10, and 29.8 we rounded to 30. So it's understandable that our approximation is a little higher because we rounded up. But because these two values are very close, for example, if you had £2,950 in a bank account and you said to your friends, I've got £3,000 in there, it wouldn't really be a lie because you'd be very close in terms of not being very far off at all. So at any rate, that calculation by using rounded values shows that the calculation is sensible. You can't just tick a box and show no working. You have to show the working for this one. Question 15, we've got a graph of y equals 4 minus x shown for us for values of x from -2 to 5. And it's shown on the grid. And we're asked to, on the grid, draw the graph of y equals 2x minus 5 for the values of x from -2 to 5. And so one way you might want to tackle this question is by doing a table of values, which I've got ready here just to show you. Now with a calculator, this isn't a very hard process, because all it is just substituting in different values for x into this formula we need. And so, just to make it clear, we've been given one graph already. The one we've been given is y equals 4 minus x, which is this one. I'm just going to colour in yellow here. The one we need to plot now is y equals 2x minus 5. Now, all you really actually need when plotting a straight line graph is just any 2 points. Take 2 points, a straight line through them, and that's all you need. And you should be able to recognise that these will be straight line graphs because they don't involve a y squared, don't involve an x squared, they don't involve the x dividing something. If a graph is in the form y equals some number in front of an x plus or minus a number at the end, it will always be a straight line graph. Anyway, so if x were -2, the first value of x, then y will be 2 multiplied by minus 2, then minus 5, which is minus 9. So when x is minus 2, y is minus 9. When x is minus 1, we can just take out minus 2 and put in its place minus 1, and we get minus 7. When x is 0, take out minus 1, put in its place 0, and we get minus 5. So we can keep doing this for all the different values of x we need. And what you should find is that the values of y increase by 2 each time. And that's no coincidence, because the number in front of the x is 2. I'm just going to briefly show you how you could do your own table of values using a calculator. So if you're serious about mastering your calculator, this is worth paying attention to. So if you press mode, then table, it comes into this mode here. Now f of x just means y. So what y are we going to want to plot? So the y we want is 2x minus 5. So we type in 2, then we need to find an x. Now the x we need is this red x here. So we press alpha, which is in red, and the bracket to get the x symbol. Then press minus 5, and that's the entire equation, so press equals. Start means the starting value of x. So x starts at minus 2. So type in minus 2 and press equals. And the graph, we can end it at 5. So press 5 and equals. Step means what is x increasing by each time. So if you have a look at this coordinate grid, x is going along in ones. 1, 2, 3, 4, 5, 6. And so we can leave this as 1, and then just press equals. Then what you're given is a table of values for x and for y. So when x is minus 2, y is minus 9. When x is minus 1, y is minus 7, and so on. And so what you should see here is this table of values. Look at the numbers for y. Minus 5, minus 3, minus 1. It's exactly what we worked out ourselves. So by taking your calculator seriously, it can save you an awful lot of bother, and can also help you to check if you've done things right. Anyway, now we've got the table of values and completed it, the only thing left to do now is to plot the points. As I said before, the only thing you need is 2 points in order to successfully plot a straight line graph. So I'm going to just take Vn2. So minus 2 and minus 9 will be this point here. And 5 would be this point here. So now we just need to do a straight line through these points, and that's the graph complete. So what we've done here is the graph of y equals 2x minus 5. Now part B says use your graph to solve 2x minus 5 equals 4 minus x. And so if we notice 2x minus 5 is what we just plotted this green line here, and 4 minus x is the yellow line. And so the green is the same as the yellow where the graphs cross. So where the intersection of the lines is the solution to this question. Big tip, it says use your graph another big tip, is only 1 mark. So the answer is going to be fairly obvious if you spot it. So once you spot that it's where they cross, which might be important, they cross at 3. And so x equals 3 when these two are the same. So x equals 3 is the solution for part B of question 15. Question 16, and we've got some angle facts to consider. First of all, BCD is a straight line and triangle ABC is equilateral. CE equals DE. And so if CE equals DE, and the line's been marked like this shows that as well, then we know for definite that this triangle here must be isosceles. Because an isosceles triangle has 2 sides that are the same, and because of that, it'll also have 2 angles that are the same. The 2 angles that are the same in an isosceles triangle are where the 2 equal sides don't touch. Where the 2 equal sides do touch, that's the odd angle out. This is the one that isn't the same as the others. So the 2 sides which are the same, often referred to as the base angles, are these two at the bottom. And so whatever this angle is here, whoops, a bit too thick a brush, whatever the angle at C is in this triangle, the angle at D will also be the same. So of course you need to know that angles inside a triangle add up to 180 degrees. So 28 plus one of those angles are highlighted, plus the other angle, which is the same size which I've highlighted, 28 plus this one, will have to add up to 180 degrees. So we can simplify this down by moving this 28 to the other side. If this 28 swaps side and joins the 180, it'll swap sign. This 28 as it stands right now is a positive number. When it moves to the other side, it will change to a negative. So 180 minus 28 just resetting my calculator there from the previous question. 180 minus 28 is 152. And so these 2 green angles combined will be 152. So if we want to work out what just one of the green ones is, what we'd have to do is divide by 2. That 2 means 2 lots of the green angle. So if that 2 swaps side, it'll swap its sign. The opposite of multiplying by 2 is dividing by 2. And so each green highlighted angle is going to be 152 divided by 2, which your calculator should tell you is 76 degrees. Like that. 76 and 76. The next thing to notice of this question is that triangle ABC is equilateral. So if a triangle's equilateral, that means all sides are the same and all angles are the same. Angles inside a triangle add up to 180 degrees. So if all these 3 angles are the same, each angle, and hopefully you should really know this, but if not, this is how you can prove it. 180 divided by 3 gives us 60 degrees. So each one of these angles here is going to be 60 degrees. Because we're told it's an isosceles. No, sorry, an equilateral triangle. Now what we've got is all the ingredients of the puzzle. We can work out what x is next. Just taking care of my colouring in. I do like a bit of colouring. Maybe I need to grow up, but never mind. Anyway, if we now just zoom in at this bit here, at C, we've got 60 degrees, we've got 76, and we've got x somewhere in the middle. Now angles that touch together at the same point and lie on the same side of a straight line will add up to 180 degrees. And so these three angles here will add up to 180 degrees. So that's 60 plus x plus 76 will have to total 180 degrees, because angles on a straight line add up to 180. So we can neaten this up a bit by just adding together 60 and 76. So if we do 60 plus 76, we should find that that's 136. And so 136 plus x equals 180 degrees. Finally, to solve for x is, we can move this 136 to the other side of the equation. But once again, if we swap the side, we swap the sign. Opposite of a positive 136 is minus 136. So therefore, x will be 180, take away 136. If we just work this one out now, comes to a total of 44. Part B, for question 16, Amber wants to work out the size of an interior angle of a regular octagon. Interior means inside. For example, interior decorating means decorating that takes place on the inside. So by interior angle, we mean one of these corners of the shape on the inside. And so she's got a method written below, which is the interior angle is 360 divided by 8. Is her method correct? Just worth mentioning as well that this diagram, if it says diagram not drawn accurately, that's not the same thing as saying the diagram's drawn terribly. Just because it's not accurate doesn't mean it's going to be completely terrible. And so what we could do is check her method and see if this is approximately right. 360 divided by 8. Is 45. So if she is right, if it was an accurate drawing of an octagon, this angle here on the inside, the interior angle, should be 45 degrees. Now if it's not accurately drawn, maybe it'll be about 40 degrees, maybe about 50, but it's not going to be way off 45 degrees. So what I'd suggest doing, just to give yourself a clue, would be to measure the angle at any case. So if we just put a protractor over the angle and measure what it is. Start from 0 and count up 80, 90, 100, 110, 120, 130, This angle here seems to be in between 130 and 140. That to me seems about 137 or 138 or so. So that's nowhere near 360 divided by 8. That's nowhere near 45 degrees. Not that you should rely on that intuition as a judgment, but I'm just saying to measure it could give you a clue, if not actually give you proof that she's wrong. Her method's incorrect. Now, if you take the interior angle calculation here, if you take 360 degrees and divide by the number of sides, that is a valid calculation. But it doesn't tell you the interior angle, that tells us the exterior angle. So she's confused the interior angle calculation for the exterior angle calculation. This angle here, 45 degrees, would be what the angle would be on the exterior. So what she's calculated is this one here on the outside. So, put briefly, she's wrong because her calculation is for the exterior angle, not the interior angle. So that would be 45 degrees, but definitely not the interior angle. So her calculation, her idea, is definitely wrong, because what she's worked out is the exterior angle instead. Question 17, we have a map, and it's a scale drawing, and we're told first of all that A is due west of B. And what we need to do is write down the bearing of A from B. With bearings, always pay attention to where the bearing's measured from. From B means we start facing north at B. So starting at B, facing northwards. Because bearings always start from facing north. We're looking at this angle here. We're going to start from B, facing north, turning clockwise around until we are facing A. And so the bearing of A from B is this angle here. Now, hopefully you should see that if that's west, if A is due west, down here would be south, and this is east. This is 3/4 of a way round the compass. This is 3/4 of a full turn. And so 3/4 of 360 will be 270 degrees. And so the bearing is 270. The bearing due east is 90, due south is 180, west 270, back north we've done a full 360. And we could check this by doing the calculation on the calculator, which should just be 3/4 multiplied by 360, which of course gives us 270. Now for part B, we've got that two different people are driving along different routes. So Umar drives from A to B on the route shown. So first of all, I'm just going to highlight Umar's route. So Umar's going from A to B like this. Whereas Kaz is going from B to C. Now from B to C is this zigzag route. So you start at B, go up until we get to that point, turn a sharp right, and go straight line towards C. So we need to use this map to work out how much further Umar drives from Kaz and show our working while we're at it. And so first of all, let's have a look at Umar's distance. It's a scale drawing, so we need to actually measure this one with a ruler. So Umar is going from A to B. So if we put our ruler starting at 0 from A and measure the distance towards B, what we should find is from A to B is 6.5 centimetres. If you're swearing blind that your map is different, or you're getting 6.7 or 6.4, don't say I'm wrong, or don't think you're necessarily wrong. It could be that your teacher's photocopying is slightly different from mine. I think the original exam it should be 6.5. However, just put down your measurement from A to B. It should be exactly 6.5, if not, should be very close to it. And if you're not sure if you're measuring it correctly, the best thing to do is just to check with your teacher. But in my example, from A to B is 6.5 centimetres. .5 centimetres is about the length of a thumb, so you wouldn't be driving that distance unless you're particularly lazy. We need to just bear in mind that we need to convert this distance to kilometres, and so using this scale here, 1 centimetre equates in real life to 200 kilometres. So in this case, we've got a small thing here, massive distance here. Small and big for comparing something which is small and something which is big. The two things we're comparing is the map, which is obviously going to be the big thing. What am I talking about? The map is going to be the smaller thing. And the real life distance is obviously going to be bigger than a map. Don't know what I was thinking just there. And this one here, this relation, is in the form where one of the numbers is 1 and the other number isn't 1. So if a ratio is ever in this form, and we can convert units by using a ratio that's given, if one number is 1 and the other number isn't 1, we change from one to the other by multiplying or dividing by the number that isn't 1. In this case, multiplying or dividing by 200. So if we're changing from centimetres to kilometres, just look at the numbers. Small number, bigger number. If we're going from small to big, we multiply by 200. And so to go the other way around, to convert from the kilometres in real life to the centimetres represented by that on the map, we'd go the opposite way round and therefore do the opposite thing. The opposite of multiplying by 200 would be dividing by 200. But going back to Umar now for a second. We've measured the distance that Umar's travelled, and Umar, according to the map, has travelled 6.5 centimetres. Now we need to convert that to the real life distance. So what we do here, to change from centimetres to the kilometres that represents in real life, we multiply by 200. .5 multiplied by 200 gives us 1300. And so Umar travels a total of 1300 kilometres. We now need to work out how far Kaz travels. Now Kaz goes along the green route, and so again we need to use the ruler and measure the distance on the map for this green route. And so he's going to be starting at B, so put the 0 on top of B, and then measure from B to C. So that's 1 centimetre, that's 2, 2.5, 2.6. That looks to me to be between 2.6 and 2.7. I would be saying that's closer to 2.7 than 2.6. And so this part of the journey from B to C is 2.7 centimetres. And the final part of the journey, we put the 0 bit of a ruler on top of that corner bit and measure to C. And that looks to me to be almost exactly 2 centimetres. Again, if your distances are different, check with your teacher that your photocopying isn't slightly different somehow. So in terms of on the map, it looks like Kaz is travelling on this route a distance which is represented by 2.7 centimetres on the map. And then a distance which is represented by a final 2 centimetres. And so on the map, Kaz's route is described by a total map length route of 4.7 centimetres. So we need to convert from centimetres to kilometres, again using the same scale factor. It's the same map we're using, so it's going to be the same scale factor. To change from centimetres to kilometres, we need to multiply by 200. .7 multiplied by 200 gives us 940. And so Kaz must travel 940 kilometres. If the map's to be trusted, of course, which it should be. So now, how much further does Umar travel than Kaz? It's just a case of working out the difference between Umar's and Kaz's distance. So the final step is to do 1300, subtract 940, to see how much further Umar's travelled from Kaz. So 1300 minus 940 gives us 360 degrees. Not 360 degrees, sorry, 360 kilometres. Random words coming into my head. So the final answer is 360 kilometres for question 17. Question 18, we have a shop that sells raincoats and umbrellas, and we've got a scatter graph to have a look at. Almost always, in fact I'd say always for a scatter graph, it's always an idea at some point to draw in a line of best fit. So there's no more points to plot, so we may as well just do a line of best fit anyway. Even if the question didn't ask us about specifically drawing a line of best fit, I'd always suggest to draw a line of best fit. And all this means is to do a straight line going through or as close to as many points as we can without going out of our way to get close to a point. If a point looks like it doesn't really fit the trend or fit the pattern, just leave it be. As a rough rule of thumb, if you're not sure where to put your line of best fit, try to aim to have roughly the same number of points above the line as below the line. And so I think if we go here and do a line looking something like that, then that will be fairly close. So you might be thinking that this seems a bit on the high side, and you know, maybe it does. However, there's about 3 points below the line, 4 or 5 above, so there's maybe could be slightly higher in fact, but I don't want to make it too high because it's a balance between having points crosses above and below the line, but also making sure that you're not miles away from lots of points. There is an exact way of doing it when you get to A level, but for GCSE it's a case of just using your own best judgment. So that line of best fit will do. And don't panic about thinking the examiner will mark you down if your line of best fit is slightly different to mine. As long as your line of best fit is roughly looking the same way and you've made a good effort, the examiner will build in what's called tolerance for awarding you the marks. So they'll allow a range of different lines of best fit. Now if you did a line like this, like in red, that'll do as line of best fit. That wouldn't do. That's just not a good line of best fit. Or if you did a line of best fit like this, again, that would definitely be a bit too low. So try and be as accurate as you can, but at the same time don't unduly stress over it. Anyway, let's have a read of the actual question, shall we? I've just been talking about lines of best fit for the last couple of minutes. Part 8, write down the type of correlation shown by the scatter graph. So if the line of best fit is going upwards, as we read from left to right, that's called positive correlation. The other type of correlation is where the line of best fit is going down as you go left to right. If it's going down, that's called negative correlation. But because this line of best fit is going upwards, we're going up the hill, that's positive. Part B, the manager expects the sales of umbrellas next month to be £60. So we need to use this line of best fit now to estimate the sales of raincoats next month. And so he's saying sales of umbrellas next month, £60. And so sales of umbrellas is along the x-axis, and he's thinking it'll be £60. What we can do is use his estimate to see and read off from the line of best fit where the line would cross on the y-axis. So if we go up to the line of best fit until we hit it, then as soon as we hit it, we go across until we get to the y-axis. And so it seems to me like £60 sales of umbrellas would correlate to approximately £135 or maybe even £130. Probably round up because it's half a square. So £135 worth of sales of raincoats. Each little square is worth 5. So that's 130. That's 135. You could even put 132 if you wanted to. So I think if you put somewhere between 130 and 135, somewhere in that region, you should be getting your mark. So I'm going to put about 132, I think. I've changed my mind. Because it's an estimate, we're allowed to have a bit of freedom. I'm going to go for 132. Your estimate should be fairly close to that. I'm not saying you need to be exactly the same as me to have the marks given to you, but show evidence of using your line of best fit like this, and as long as your line of best fit is accurate enough, you will get the marks. Question 19. Multiply out x bracket x minus 4. So we take what's on the outside of a bracket and multiply by what's on the inside. So first we'll do x multiplied by x, which gives us x squared. And then x multiplied by 4 is 4x. But because this is a minus sign, we need a minus sign in here. So x squared minus 4x is what we'd get. Therefore we need to circle this third option. Question 20, we've got the ratio of a to b is in the ratio of 5 to 2. How many times larger is a than b? So how many times larger is 5 as compared to 2? So here these numbers are slightly awkward. What you could do is change the parts for b from 2 parts to 1 part. To go from 2 down to 1, we could divide 2 by itself. Remember, any number divided by itself gives us 1. But with ratios, what we do to one side, we need to do to the other to keep the proportion in balance. And so 5 divided by 2 would be 2.5. Now this is much more useful and powerful because this tells us for every one lot of b, we've got 2.5 times as much for a. And so to change from b to a, we'd have to multiply by 2.5. And so a is 2.5 times the size of b. Another way we could have done this one would have been to have just done 5 divided by 2 on the calculator. Compare the large to the small. Large divided by small will tell you the scale factor if you like. And that's 2.5. Question 21. We've got a circle that has radius of 4.2 centimeters. We need to work out the circumference. Now there are two main formulas I should say, for circles, and they both involve pi. Now talking about pi makes me hungry because I think of food. So one type of pie I quite like is chicken. Chicken pie's delicious, in fact. Also, after having a chicken pie, I like to have an apple pie. Chicken pie is delicious, apple pies are too. And credit to Simon Ferris for that one. The great Simon Ferris. So now, we need to think which one we're going to be using. Is it the circumference formula or the area formula? Well, it says here to work out the circumference, and so we're going to pick the top equation, because C stands for circumference. So what I've got here is a diagram of a circle, so we can just label what we know. So if we do this, radius is 4.2. Now the radius just means from the middle going towards the outside, from the middle outwards. So the radius of this circle is this distance here, which is 4.2. Now the diameter relates to the radius because the diameter is always double the size of what the radius is. So if the radius is 4.2, and that's just half the way across, the diameter, which is all the way across from one end to the other, will be 4.2 times 2, which is 8.4. So using this formula here for diameter, C equals pi multiplied by the diameter. Now we just worked out that the diameter is 8.4 because it's double 4.2. And so the circumference is just going to be pi multiplied by 8.4. So if we just get the calculator and work this out, shift x 10x to get the pi button, multiply by 8.4, and we get an answer in terms of pi. Here we give the answer to one decimal place, so convert to decimal form, and we've got 26.389, and so on and so on. The number will keep going on forever, but we want it to be rounded to just one decimal place. So if we just cut off a number and leave just the first number after the decimal. That's one decimal place. And so the answers might be 26.3. But to decide if we stay as we are or if we round up, we look at the number immediately to the right of the number we're rounding to. So next door to the 3 is an 8. Now if it's 5 or higher, we round up. So that 3 will round up to a 4 because the 3 is next door to an 8. So it's one decimal place, we've got 26.4 centimetres. In part B, draw a sector of the circle. A sector just means a slice taken from the middle. And so here's one I made earlier. That's a sector of a circle. So it doesn't need to be this size, just any slice, like a pizza slice, taken from the middle of the circle is called a sector. You could have done a much wider one, or you could have done a thinner one. But just one slice taken from the middle, two radiuses that's joined to the circumference is a sector. And that's all you need to do for part B. Question 22. We've got a tree diagram to complete. About two ordinary fair dice that are rolled. The main thing to know for a tree diagram is that where the tree branches from, the two branches, or no matter how many branches it branches from, will all add up to 1. So this one here is 1/3. This one here must be the other 2/3, because 1/3 plus 2/3 gives 1. So the total of all branches that meet at the same point will always need to add up to 1. And because this one's 1/3, this one will be the same as well, which is 2/3. The second dice, this one's going to be the same but just hasn't been completed for us. And so the chance of rolling a fair dice and getting less than 3, well, if you think about it, because this is based on something we can relate to, dice, how many sides on a dice are less than a 3? Well, there's a 1 or there's a 2. And so 2 sides out of 6 are less than a 3. And that simplifies down to 1/3. And so this is where the numbers 1/3 and 2/3 are coming from. So the first mark is just for filling in the missing values in the tree, like this. Part B, we need to work out the probability that both dice land on a number less than 3. So the probability that both dice land on less than 3. That can only happen one way. It's a probability that the first is less than 3, and the second dice is less than 3. And so, with probability, if we have an and, probability of one thing and another, it means we multiply the two probabilities together. So what we do now is probability for the first is less than 3, multiplied by the probability that the second one is less than a 3. So let's look at the diagram to work this one out. So the probability that the first dice lands on less than a 3. This is the first dice. It's 1/3. And then the probability of the second one is also less than a 3. The second dice being less than a 3, that's also 1/3. And so all we're going to need to do here is 1/3 which is probability of the first dice landing on less than a 3. I'm going to multiply that by the 1/3 chance that the second dice is also less than a 3. So 1/3 multiplied by 1/3 is the calculation we need to do now. 1/3 multiplied by 1/3. Press equals, we get 1/9. It's 1 in 9 chance. And that's part B done. Question 23, we have to match each sequence to its description. One's been done for you. So we've done a Fibonacci sequence. A Fibonacci sequence means that each term is the sum of the two terms before it. So if you have a look at that 2, that comes from doing 1 plus 1 before it. This 3 is from the 1 plus 2. 5 is from 2 plus 3, and so on. Now, I'm just going to remind you of what different sequences mean, because it's worth knowing if this sort of question ever comes up similar again. So first of all, it mentions an arithmetic progression. Well, an arithmetic progression is a sequence where the gaps between the numbers is the same. We just add in the same amount each time. And so, using that fact, we can now look and see which one of these has got gaps which are equal. The only one which has got gaps which are the same is this one here. This one's going up in 1 each time. And so this one is the arithmetic sequence for that reason. One, 2, 3, 4, 5, 6 is an arithmetic progression because the numbers are going up by the same thing, or they could be going down as well, going up or down by the same amount each time. And in that case here, the numbers were going up by 1s each time. Now, the other one that's mentioned is the geometric progression. Now this one is where the gaps between the numbers aren't the same. With a geometric progression, it's a sequence where each number is the previous one multiplied by a fixed value. So with an arithmetic progression, we're adding the same amount each time. With a geometric progression, we're multiplying by the same amount each time. So for example, the numbers might be doubling as we move along, the numbers might be tripling, each number might be 5 times bigger than the last, and so on. So if we have a look at these sequences here, this one here, if we double 1, we get 2, double 2 we get 4, double 4 we get 8, double 8 is 16. This one here is a geometric progression because the numbers are being multiplied by the same amount each time. So in this case here, the numbers are just being multiplied by 2 each time. 1 times 2, 2 times 2, 4 times 2, and so on. And so the geometric progression is the one I'm just highlighting in green. Now, square and cube numbers should be the easiest ones. Squares and cubes should be the numbers you see each time. Each time you're in a math lesson, you probably see squares or cubes somewhere, or most math lessons anyway. So, square numbers, we can generate with a calculator if you forget them. 1 squared, the first one is 1. The next square number is 2 squared, which is 4. The third squared number, 3 squared, which is 9, and so on. But really, you should know the square numbers off by heart up to 15 ideally. So the square numbers is this one here, 1, 4, 9, 16, 25, 36. Wrong colour pen. Those are the square numbers. So we join these up. The cube numbers we get by doing whole numbers multiplied by the power 3. So 1 cubed would be 1 to the power 3, which is 1. The next cube number will be 2 cubed, which is 8. The next one would be 3 cubed, 3 times 3 times 3, which is 27. So 1, 8, 27. This one at the bottom is the cube numbers. So we join these two up. And therefore the only one which hasn't been joined up is this one, so these must be the triangular numbers. I'll just briefly explain why 1, 3, 6, 10, 15 and 21 are the triangular numbers, in case you're interested. Triangular numbers are just numbers we can make that form triangles. So 1 is a triangular number because that in a way is a very small triangle with just one thing inside it. The next one, we can make a triangle using 3 circles. We can make a triangle using 6 circles, or if you ever go 10-pin bowling, the triangle's set out like this. So each row we add one more circle than what was in the previous row. So 1, 1 plus 2, 1 plus 2 plus 3. The fourth one, 1 plus 2 plus 3 plus 4. And so that's where the term triangular numbers comes from. Question 24 is a percentage change question. So you've got a population of a city in 2001 and 2011. And so Liam's saying that from 2011 to 2021, the population of a city will increase by the same percentage as from 2001 to 2011. So he works some stuff out. He works out that from 2001 to 2011 is an increase of population of 60,000 people. So he thinks it'll be the same population increase again. So we need to see if his claim's correct. And so by his claim is this thing here, that the population of a city will increase by the same percentage. So we need to find the initial percentage change. So from 2001 to 2011, we can calculate directly the percentage change. Percentage change, we can calculate this formula for any sort of percentage change. The percentage change is the actual change as a fraction of the original value then multiplied by 100. And so the change we can work out by just taking the population in 2011 and subtracting it from the population that it used to be in 2001. And so the change is 480,000 minus 420,000 over the original value. Original is the starting population, so for this particular question it started off being £420,000. So for the time period 2001 to 2011, the original in this case is 2001, because that's where we're starting from. So that's the fraction. We need to multiply that by 100. And that'll give us our answer. So we can simplify this down first, this fractional part, or with a calculator we can just type it in as it is. 480,000 minus 420,000. All of that divided by 420,000. And then that multiplied by 100. So to one decimal place, roughly speaking, that's a 14.3% increase. So for the first 10 years, from 2001 to 2011, we had a 14.3% increase. So now, if Liam is correct, the population in 2021 should be population in 2011 plus the same 14.3% increase, if he's right. So we can work out 14.3%. 14.3% means 14.3 out of 100. 14.3% of the 2011 population will be this percentage of 480,000. So if we work this out here, %, of 480,000 comes to roughly 68,640 people. So the population in 2021 would be the 480,000 plus this same percentage increase, which we just calculated above was 68,640, and that gives a total of, or an expected total, of approximately 548,640 people. But according to what he's worked out, he should be expecting 540,000 people. And so this is different. This is not what he worked out. So essentially, it doesn't match his claim. So it's not 540,000. as he worked out. And so the final answer to this is no. He's not right. It doesn't match his claim. He's thinking that the amount will increase by the same each time. 60,000 increase from 2001 to 2011, and the same increase again. But just because it's the same percentage increase is not to say that the actual amount the increase will be the same as well. So, unfortunately, Liam's claim doesn't add up. Question 25. Ali throws darts at a target. So for part A, we need to work out two different estimates for the probability of Ali hitting a target. The good news of this is we've got four possible different estimates we can take. One estimate is on Monday. So if we estimate for Monday, the probability of him hitting a target, the best estimate is looking at the actual experiment of how many throws he's had compared to how many hits he's got with those throws. So on Monday, his hit rate was 15 out of 20. (15 out of 20 hits). So that's roughly 15 out of 20. Well, that's exactly 15 out of 20 actually. And so, estimating from Monday, we could say that we'd expect the chance of him hitting a target to be 15 out of 20, 3/4 of the time he hits a target. Or we could pick Tuesday. So based on Tuesday, he hits 22 out of 30. So that means 22 of a possible 30. On Wednesday, same idea. Based on Wednesday, he only hit 17 out of 40 though. So Wednesday didn't have a good day. 17 out of 40 hits makes out that he's less than 50% likely to get a hit. Because 17 out of 40 is less than half. He hits the target less than half the time on Wednesday. Or we could do an overall. These are the overall stats. So overall, he hits 54 out of 90. As a fraction, that's 54 over 90. So based on the table we've got here, we've got an estimate based on Monday's data. There's an estimate based on Tuesday's data. We have an estimate based on Wednesday's, which was a bad day where he got 17 out of 40. And also there's an estimate based on the overall statistics. And so all we need to do here is actually just to pick any two of these four. There's four different ones we could pick. Pick any two of these four. So I'd be suggesting that to pick the overall, first of all, because the overall has got the most data in it. It takes into consideration all the throws. So 54 over 90, and Wednesday seemed to be the odd one out. I'd pick, for example, maybe Tuesday or Monday. So it doesn't really matter as long as you pick any two of the four. So I'm going to pick Tuesdays. So from these four colours I've highlighted, purple, green, yellow or blue, pick any two of those four for your estimates. In part B, we need to compare these two that you've chosen. It says which of your two answers is the better estimate for the probability of Ali hitting a target. Give a reason for your answer. No matter which two you've picked, the most reliable will be the one with the biggest denominator. It will be the probability estimate which takes into consideration the most throws. So in my particular case, the most reliable will be 54 over 90. And the brief reason is takes into consideration a greater number of total throws than the other estimate. Teachers tend to like to talk about the number of trials increases the accuracy of an experiment. So by trial we mean here how many times the experiment's repeated. In his case, how many times the darts are thrown. So the more throws we can go off, the more reliable the data. So 54 out of 90 takes into account 90 throws. I'd rather go off 90 throws than go off 30 throws. Question 26 is a ratio question. We've got Theo and James who are trying to save some money. So Theo starts with savings of £18. James has nothing. And each week from now, we're told that Theo will save £4.50 and James is going to save £4. In how many weeks will Theo and James have savings in the ratio 15 to 8? This is a question where it's really hard to know where to begin. So there is quite a complicated algebraic method you could use, which I'm not going to mention and I'm not going to go into. My strongest recommendation for you would be a type of trial and improvement approach. And just to think it through, there's a table of values. So start off with what the question says they start off with, where Theo's got £18 and James has got 0. Then build up the amounts week by week and see each week if the ratio is 15 to 8 yet. So after 1 week, Theo will save £4.50. So in 1 week's time, Theo's savings will be £18 that you started with, plus an extra £4.50. So Theo, after 1 week, will have £22.50. Whereas James will have £4. Now we can compare ratios using a calculator as long as we put the smallest number at the top. So for example, if we put £4 on top and the £22.50 at the bottom, the ratio is 8 for James, 45 for Theo. And so is the ratio 15 to 8 yet? No, it's not, because checking of the calculator, the ratio is 45 to 8. So let's go again. Let another week pass. So Theo's going to save another £4.50. So £22.50 plus £4.50. Gives a saving of £27. Whereas James has now saved another £4, which takes him to £8. So let's compare the ratio of 27 to 8. So again, on a calculator, if we put the small number on top, the big number on the bottom, that doesn't simplify. And so this ratio now is not 15 to 8, it's just still 27 to 8. So go again. With a calculator, this trial and improvement method isn't half as slow as it would be without a calculator, because we can just keep on adding £4.50 for Theo, which with a calculator is very straightforward. And with James, it's just the 4 times table. So let's see now on week 3. The ratio is 31.5 ... So put these numbers into a fraction, smallest number on top, bigger number on the bottom. That's a ratio of 21 to 8. So it's still not 15 to 8 yet, but we are getting closer. The next one, 36 ... 16 goes to 9 ... 4. So again, that's not yet 15 to 8, it's 9 to 4. If we try week 5, this ratio of £40.50 to £20, and see what this comes out to be. Small number on top, big number on the bottom. We get 40 over 81. So again, that's not right yet. And if we go again, add another £4.50 on for Theo, £40.50 plus another £4.50 is £45. And then for James, add on another £4, which is £24, and see what this would be simplified. 24, 45 becomes 15, 8. So actually that does work. And so in how many weeks will Theo and James have savings in the ratio 15 to 8? We've just calculated that. They have savings of 15 to 8 after 6 weeks. So final answer is we need to put after 6 weeks. They'll have savings in that particular ratio. Question 27. We're given the formula for the volume of the sphere. It's 4/3 pi r cubed. And we've got a container which is in the shape of a hemisphere. Sand fills the container at a rate of 4,000 cm cubed per minute. Does it take less than a quarter of an hour to fill the container? You must show your working. Well, let's work out the volume of the sphere. If you think this diagram looks different to one you've got in front of you, don't worry, I will explain. So for this sphere, the volume of the sphere is 4/3 times pi multiplied by the radius, which is r, cubed. So just remember that r is the radius, and we're told that it's 30 centimeters. So if we just whack these numbers into our calculator, 4/3 multiplied by pi multiplied by 30 cubed, we get an answer of 36,000 pi, which as a decimal would be 113,097. Don't round off numbers halfway through a calculation, so I'm going to just put down all these numbers. 113,097.3355. So that's the volume of a sphere. But have a look at the shape in front of you. How is your shape different to the one I've got here? And importantly, we're not talking about a sphere, are we? We're actually talking about a hemisphere. And so what we need to do is we need to cut this shape in half. We need to slice it in half to get a hemisphere. Hemisphere means half of the sphere. And so if I were to do that and just slice it in half, ta-da, we'd have this shape. This is a hemisphere. So I'm just trying to make the point clear that we need to half it. A common mistake for this question is to apply the formula, but then to forget to half it. So if the volume of a sphere is this, and the volume of a hemisphere will be exactly half of what we've just worked out. Hemi sounds a bit like semi, and semi means half. That's not a coincidence. So volume of a hemisphere will be this number here, that long awkward number, divided by 2. Because we're not talking of a sphere, we're talking about a hemisphere, so we need to divide by 2. And so if we just take this number we had in our calculator and half it, we'd get 56,548. And write down as many digits as you can. Don't round off halfway through a calculation, otherwise some rounding errors could creep in. Round off only when you're absolutely confident, but it's safe to. If you're not sure whether to or not, only ever round off at the very, very, very last step, just before you put your final answer down on the answer line. Anyway, that's .66776. And the units for volume, because we've used centimetres going in, we'll have cubic centimetres coming out. Sand fills the container at a rate of 4,000 cubic centimetres per minute. And we need to answer if it takes less than a quarter of an hour to fill the container. So, one thing we are told is that each minute it gets filled with 4,000 cubic centimetres. So 1 minute we can fill this much. So in quarter of an hour, well, how many minutes is a quarter of an hour? A quarter of an hour would be a quarter of 60, which is 15 minutes. So 15 minutes is 15 times longer than just 1 minute. So if it's 15 times as much time, we could fill 15 times as much volume of sand going into the container. If we multiply this number by 15, we need to multiply this number by 15 to keep the balance. So 4,000 multiplied by 15 would be 60,000 cubic centimetres. And so what that tells us that in 15 minutes we'd be able to fill up 60,000 cubic centimetres worth of sand. But because the volume of the hemisphere is less than 60,000, it's about 56,500, it wouldn't take all of those 15 minutes to fill it up. It'd only take maybe about 14 minutes or so, because you don't need to fill all of that 60,000 cubic centimetres. And so when we're asked, does it take less than a quarter of an hour? Yes, it does. It takes less than a quarter of an hour. There's less than 60,000 cubic centimetres that needs to be filled up. Finally, now question 28, we have error intervals. Once you get your head around error intervals, they are not half as bad as what you might think they are. I'll try to explain now. So the length of each side of a regular pentagon is 8.4 centimetres to 1 decimal place. So that means the length has been rounded to 1 decimal place. In fact, I'll use a different colour. 1 decimal place has been rounded to this number here before. And so what we need to think about is what's the smallest possible length we can imagine but would still round up to 8.4 when we round to 1 decimal place. It would have to be 8.3 something. 8.36 would round to 8.4, as would 8.37. The smallest possible number you can have which still rounds up is a 5. 5 or more is when you round up, but any less than 5 is where you wouldn't round up. So the smallest possible length it could have been before being rounded would be 8.35. And the longest length if it were 8.45, that would round to 8.5, so the longest length absolutely has to be less than 8.45. And so the limits for the length are 8.35 as the smallest possible length it could be, up to 8.45, which is the absolute and utter limit, which it can't actually be. It can be anywhere up to 8.45. It could be 8.4999999, but it couldn't actually be 8.45. So it could be 8.44 with infinite nines almost, but couldn't be 8.45. If you have a look at the answer to the error interval compared to the number which has been rounded, we take the 8.4, and this will almost always be the case with error intervals, the form they take. You keep this number the same, and the upper limit is the same number with a 5 just plonked on the end. Same idea for the lower limit, just plonk a 5 at the end, but the number in front of the 5, just make it 1 less. So 8.45, 8.35. Now for part B, we need to complete the error interval for the perimeter. And so what's the smallest possible perimeter? What's the largest possible perimeter? Well, the smallest perimeter will be when the lengths are at the smallest. So when the lengths are 8.35, that's the smallest possible perimeter. Whereas the largest perimeter would be when the lengths are very, very close to 8.45. Now it says here it's a pentagon. Just in case you forgot what a pentagon is, I've got some drawn here for you. A pentagon is a 5-sided shape. So the smallest possible perimeter, if each side was 8.35, the total perimeter would be 8.35 multiplied by 5. 8.35 multiplied by 5 would be 41.75. So the smallest perimeter is 41.75, whereas the absolute maximum perimeter would be when the lengths are at the absolute maximum, so up to 8.45 multiplied by 5, which is 42.25. So the perimeter must absolutely be somewhere between these two values. That's the absolute smallest possible, that's the absolute limit to the biggest possible. So error intervals definitely worth revising, because once you get your head around them, they're actually, relatively speaking, straightforward. But that's question 28 completed, and also therefore the entire paper. So I hope you found that useful to an extent. Do feel free to subscribe and leave any comments, and I'll hopefully see you in class sometime very soon.